I kind of wake up every day to sort of think that maybe my research is going to help someone's life. And I think this is kind of like, oh, wow, what a great person you are. But like, I think I'm going to tell you like a small story. Maybe this is...
Please.
You can cut it out if it's not relevant. Let's go to 5000 BC. Trying to explain, like, I'm time traveling back then, trying to explain the motion adaptation model to them. They'll be like, go away. Like, what are you talking about? This is not, I don't understand anything. So these models are not real models of the brain. Like, I don't know. How is the network failing? How do we know it is failing? And like, what could be the additions that you can make to the models that improves it? I think to actually have a good quantitative, tangible grasp on those questions, I think you need a platform like BrainScore to actually be there. This is the model that tells you that what is going to be the predicted neural response for any given image. I think that's where we are in the sense that we think of this as a stronger test of the model, because there are many models then that can come up with different images, then you can test those as well.
This is Brain Inspired.
Hello, good people. I'm Paul, attempter of good personhood, master of none. Today I bring you Kohitij Kar, who also goes by Ko, master of core visual object recognition. So Ko has been a postdoc for the past few years in Jim Dicarlo's lab. And if you'll remember, I had Jim Dicarlo back on episode 75, talking about the approach that his lab takes to figure out our ventral visual processing stream and how we recognize objects. And much of the work that Jim and I actually talked about was done in part by Ko. Now Ko is an assistant professor at York University, where he'll be starting his lab this summer. His lab is called the Visual Intelligence and Technological Advances Lab, and he's part of a group of people who were hired into a fancy new visual neurophysiology center at York that is going to be led by none other than my previous postdoc advisor, Jeff Schall. So Ko and I kind of continue the conversation about using convolutional neural networks to study the ventral visual processing stream. And on this episode, we talk about that background a little bit and also Ko's ideas for where it's going. So as you may know, what started out as a feed-forward convolutional neural network has since been extended and expanded, and Ko continues to extend and expand both the models to account for object recognition and experimental work that will be used in conjunction with the models to help us understand visual object recognition. And that includes adding other brain areas and therefore models to more wholly encompass an explanation of our visual intelligence. So I get Ko's thoughts on what's happening, what will happen, and how to think about visual intelligence, and a lot more topics. I link to his lab, and he is hiring, as he says at the end, so if you're interested in this kind of research, you should check it out. I link to it in the show notes at braininspired.co/podcast/122. Thank you as always to my Patreon supporters. If you decide you want to support the podcast for just a few bucks a month, you can check that out on the website at braininspired.co as well. All right, enjoy Kohitij Kar. Ko, are you an electrical engineer? Are you a neuroscientist? What the heck are you?
Yeah, I think I'm an electronics engineer according to my undergraduate education and training. And then sort of I moved slowly, gradually into like biomedical engineering, one step towards neuroscience maybe, and then finally did a PhD in neuroscience.
What was it that got you interested in neuroscience?
I think like a lot of us, I think those were discussions about consciousness and things like that that I kind of cringe upon a little bit now. But those were the introduction to neuroscience. And I think I particularly got influenced by a lot of these very nice storytellers. Like, so I was doing my master's at New Jersey Institute of Technology, but I was sort of cross-registering for courses at Rutgers, where Yuri Buzhaki was a professor back then. And just like listening to him and the way he talks about the brain, I think those were sort of the initial hooks to like, I really want to be in this field and be with these people and like talk about the brain with them. Things like that, like sort of at a very artificial, sort of superficial level. mostly. And I remember going to one talk from V.S. Ramachandran at Princeton, and it was like those kind of things was like, wow, like this is such a interesting system, and I want to work on it. And I think that were the initial things that kind of like drew me towards studying the brain.
The storytellers.
The storytellers, pretty much. And I think now I'm kind of like thinking there could be something beyond storytelling, and like, but I mean, the storytellers are perfectly fine scientists, and they also do a lot of stuff that I kind of do now. So like, there's nothing against storytelling, but I think that component that I sometimes kind of feel like, oh, what is the use of that? I think it's really useful, because like to tell a story about your science in a way that sort of attracts young minds, I think is very useful.
But now, so consciousness and storytelling drew you in, but now you've discarded both of them as frivolous.
I don't think I've discarded them as frivolous. I just have, I think my time is spent better doing other things than that. I don't think those are like bad problems to work on or like useless things. I think they're actually very useful, but I kind of realized that that's not my sort of, forte. Like that's not my expertise, is not doing that.
What percentage of people do you think who, are drawn in because of like the big questions like that? And then, I said discard or, whatever I said, but then go on to realize, start asking very specific questions and kind of leave those larger things by the wayside. It's a really high percentage, isn't it?
I think so. I think it's like a very high percentage.
Yeah.
But I think also it probably is useful to kind of keep reminding ourselves what the big questions are, and like, so I think that's simultaneously very important. And it's just that sorry.
No, that's fine. I was just going to say that I think part of the reason, and I don't really know the whole reason, but I think part of the reason is that those big questions get you in, and then you realize that there are a lot of big questions that are super interesting that aren't those questions. I don't know. Does that seem on point?
I think that's right. And I think that's kind of like very similar to how I feel right now. And I know that it's sort of like said multiple times that it's all about like asking the right questions, and like the questions are very important. But what, at least from my perspective, I think I realized that like the answers and what do I consider as satisfactory answers to those questions often determine like how you approach your science and things like that. So to me, like, it's just not about the question. It's also like, what kind of answers am I satisfied with, and why am I seeking that answer? I think those are the real drivers of what I actually do in the lab.
Yeah.
Of course, I would like to simulate, consciousness in an artificial system, but I think that is going to be a very difficult, kind of objective to, go for in a lab and get funding for it. I mean, I'm really happy that some people are trying to do that who are more privileged than probably I am. But
congratulations on the new job. I guess it's not so new now, but where are you sitting right now? You're not at York yet, are you?
No. I'm still in Cambridge, Massachusetts, at MIT, McGovern Institute.
When are you headed to York?
Yeah, I'm starting in July 2022.
Oh, nice. Well, congratulations.
Thank you. Yeah, I'm very excited, and it was a very interesting hire because all of this happened during the pandemic.
Yeah.
I'm still supposed to go and see the department to some degree.
Oh, wow.
So
yeah.
It's really virtual, remote, but I'm very happy so far with what all the discussions that I've had with colleagues there, and I'm very excited to start working.
You'll be near my postdoc advisor, Jeff Shaw, up there. So
yes, he's great, and I'm very much looking forward to working.
Tell him that I've asked him a couple times. He's been pretty busy because he just moved to York as well. Tell him that I'm still waiting for him to come on the podcast. So
okay, I'll tell him.
So your most recent work was a postdoc in Jim Dicarlo's lab, and Jim's been on the show, and you guys are.
Yep.
One of the reasons why I asked you about your engineering background is because you guys are quote unquote reverse engineering the visual system.
Right.
I guess it all started off with convolutional neural networks and the feed-forward story of convolutional neural networks. But I don't know how you got into deep learning, but I do know that you were discouraged at one point from studying deep learning or using it. Can you tell that story?
Sure. Yeah. So, I mean, it's an old story. It's like probably like now already 10, 11 years old. This was 2008 when I started my master's in biomedical engineering. And I think I kind of realized talking to a lot of people back then is that even saying the word or saying something like, oh, I'm working with a computational model and I'm in a neuroscience, program, it's sort of like you're looked down upon as a fake neuroscientist. You're not one of the real people that is doing the real neuroscience.
Experiments? And because you're not doing experiments?
Because at that time, I was not doing experiments and I was mostly trying to like look at things like, for example, like, I was doing like working on autoencoders or neural network models trained with backpropagation, basically looking at how internals of these networks might match some neurophysiological data that I had or some behavioral data, aka the things that everybody, including me, is all excited about these days. But
that was before the quote unquote deep learning revolution in 2012, right? So
it was, I think it was still popular back then among certain groups, I guess, but I just did not, I couldn't have predicted that if I had worked on that, maybe there could have been some nice papers or nice, studies, that I could have done. But as I was saying that, like, I kind of got a bit discouraged because like I just started realizing that, oh, this is not the real neuroscience because I'm not sitting there with a slice of a mice brain patch clamping and like looking at neuronal voltages going up and down on a stupid monitor or something. Like I kind of felt like, that's the real deal. And I remember I prepared a poster for a conference and I was going to present, this poster, which is work done with like these artificial neural networks. And I think I was so, I was afraid that I will be ridiculed at that conference. And in the morning of that day, I kind of just got out of there. I was like, I'm not going to present this. Forget about it. I'm going to go back and I'm going to do real neuroscience and look what I'm doing right now. So, I have unfortunately, it's really ridiculous, but it's kind of pathetic. But there's a paper that I wrote back there with all these ideas of like, backprop, like, reinforcement learning, autoencoder, student-teacher network, and it's really badly written, and don't look at it. But like, I kind of use that as a joke with my friends, like, only if I had, pursued this, like all this work from Dan and Jim, like, I was way before there. Anyways, it was, yeah.
Did you tell
it was
Jim
ridiculous and pathetic. No, I don't think he would take that seriously. That paper is a joke.
Yeah. Well, you were talking, so real neuroscience, that's interesting because what you described with the mouse brain slices and patch clamping is exactly how I cut my teeth in neuroscience because I was a real neuroscientist.
Right.
Do you think the definition of what a real neuroscientist is has changed now so that people, doing what you do is, do you feel like a valid neuroscientist now?
Yeah, well, I kind of validated myself by doing monkey physiology and like perturbation. So whenever I'm doing that, whenever I'm leading that life, I feel like as a real neuroscientist. I still think that like actually it helps to look at the brain and the biological data to get the right perspective about the system. So I definitely value that. But I think with time, the importance of computational techniques and analysis techniques are so important now. I think as we were discussing, like there's an answer that we are seeking, and that answer to me is going to be in the form of that, those models. And so like, if you're not talking that language, it sort of becomes difficult to communicate. It will become difficult to communicate any neuroscientific finding in the future. So I think in that regard, that might become the real, talk of neuroscientists in a few years, if it hasn't become that already.
You're looking for an answer. What's the question?
That's a very good question. So I think, exactly. So the question that I think a lot of people are interested in is that how do we solve certain tasks? Like at least that's the way how I look at formulating questions. Like I'm interested in neuroscience because I'm interested in a behavior, and why I'm interested in that behavior particularly, maybe because if that behavior goes missing, I'll be in deep trouble. So like that's kind of my sort of way of getting into this space of like, okay, there's a behavior, then what does it mean to do a behavior, and how do we actually scientifically study it? So we measure this behavior, we operationalize that behavior with some task, and we measure that. And then the understanding or the question is that like, how does the brain solve that problem or give rise to that behavior? And then we start by building models of that behavior. And depending on what type of answers we're looking for, are we looking at how different neurons come together and produce that behavior, or how different brain areas are participating in that behavior? We try to build specific units or parts of that model and look at them carefully. So at least that's how I formulate the questions. Like the bigger question is like, okay, there's a big behavior, and how are we actually solving it in our brain?
Well, so you can correct me if I'm wrong here, but the story as I see it from Jim's lab and from the convolutional neural network work is that, you're trying to solve core object recognition. Right. And, it started off with a feed-forward neural network, that was built through many years. And then, the deep learning world came on the scene, and you guys realized that these networks accounted well for, predicted the brain activity well, and kind of went on from there. But things have developed. So the reason why I asked what the question was is because, it's interesting. It's almost like an isolated system, right? So you have this convolutional neural network, and it is modeled, the layers are modeled after the ventral visual processing hierarchical layers in the brain. And, the goal is to understand vision, right? And I don't know what that means. Do you feel like you guys have where are we in understanding vision?
Yeah, I think that there's a lot of questions in that those sentences, because let me maybe explain a little bit about what I think of what understanding means. Maybe I think one definition of understanding that I have in my head is that it is basically coming up with a falsifiable model of something. Like if I understand something and you can tell me that it's a wrong understanding, and if I can basically have a model that is falsifiable, which I can make predictions and you can tell me that, oh, you're wrong. So for example, and there could be different levels of this understanding. So I understand how my coffee machine works because I can predict which button to press and the coffee is going to come out. So it's like a concrete prediction. You can test me you can tell me go turn on the coffee machine. Go press the wrong button. You're like, you don't have any understanding of how this machine works. But if I press the right button and the coffee starts coming out. But then if the machine breaks down, there's a different level of understanding. I might need to fix it. So then you might ask me which part of the machine to fix and how does it work, and there's a more detailed level of understanding required. So in the same way, I feel like understanding vision would require multiple levels, and I think one of it is at the behavioral level, can I predict a behavior? So that's where we but all of this sort of relies on models, concrete computational models. At least that's what my current sort of, I was going to say understanding, my current sort of opinion of what understanding for me might mean is that you have concrete computational models that make explicit predictions about, how a system is going to work or perform. And then you get to test it. And that's sort of the understanding, and then that's moving. Now, the problem I think usually is that if we define understanding this way, then we have to also sort of have common, goals of what are we trying to understand? What is that behavior? And my current, view of the field is that we actually don't have common goals like that. We are kind of all doing our own things. And so I think it's kind of important to maybe have certain specific goals as this is what we are trying to predict. These are the behavior of the system. These are the neural data or something that we are trying to predict, and then come together, come up with what are the best models that can do that. And some of it is, we are currently trying to do it with this, website and platform called BrainScore, and trying to have an integrative approach to all kinds of data and all kinds of model and things like that. So
how's BrainScore going? Are a lot of people using it?
Yeah, I think the user base of BrainScore is definitely increasing, and I think we are having a conference now. We still submitted it at Kohitij, and we are potentially going to have a competition. It's I think it's going to feel a little bit more like an ImageNet competition or something like that. But my personal opinion is that maybe someone can look at BrainScore and say it's too early for someone to start making these models or scoring them and being so concrete about it.
Right.
But I think it has to be done. That's kind of my goal. And it's, if you ask me where vision, understanding of vision is, to me, pointing to some kind of platform like BrainScore is a concrete answer that I can give. Like, that's my way of quantifying it.
Well,
so
so it's a benchmark. But on the other hand, benchmarks have gotten some flack because, like you were talking about, we don't know whether that's the right benchmark, right? Whether it's the right question.
Yeah.
So it is concrete, but I guess we're progressing and asking better questions. Would you agree with that?
Yeah, absolutely. And I think there is no like 3 or 4 benchmarks that will define our understanding. So I think the goal is to have more and more benchmarks, and hopefully we will see that, like, because it's the same brain that is giving rise to all that data. So if you're actually modeling that particular brain, then we should be converging to like a very small space of models eventually. At least that's the dream. So of course, like, there could be multiple different benchmarks and different ways people are probing the system. But I think the value add of BrainScore is that if we can get all those experimentalists and modelers on board, then they can provide those data or provide those sort of benchmarks as also targets for current systems, instead of saying that, like, oh, your network is never going to predict that. Like, that's fine. I mean, the networks are falsified under all possible benchmarks. So it's not a big, sentence to say, but it's just like, how is the network failing? How do we know it is failing? And like, what could be the additions that you can make to the models that improves it? I think to actually have a good quantitative, tangible grasp on those questions, I think you need a platform like BrainScore to actually be there.
I wanted to ask you about falsification because you've talked about how that's one of the useful parts of the modeling push is that they are falsifiable. But then, you have models like the feed-forward convolutional neural network that predict, what is it, like 50% of the neural variance, somewhere around there?
Right. Yeah.
How does one falsify a model?
Yeah, so I don't think, I mean, in the sense of falsification, those models are all falsified anyways. But then the question is, how do you build the next best model? When I think of that, I feel like given some numbers like that, it then makes me kind of figure out, if I build a better model, it should at least be better than the current numbers that are coming out of, the feed-forward neural networks or something like that. So I think, of course, the question is, like, do you dismiss the entire space of models or family of models as like completely useless, or do you say, like, that's a good start, let's build upon that and start adding elements to that to build the next best model? So I think I'm mostly motivated by this idea that, like, we have a good grasp, and thanks to machine learning and AI for actually building these real models and not like toy models. And so now that we have these models, let's capitalize on this momentum and get going and build the next best models. Although I'm talking about models in this way, but my personal, life is mostly spent doing experiments trying to put holes on that, on those modeling frameworks or models. So I'm actually very happy that those are all falsified, because I feel like that's my job to falsify them. But the other part of my job that I feel like is important is that it's not only just to falsify them, but also get some data that is in the same scale and in the same sort of spirit that would help build the next best model or something. So it's just not good to shit on them. It's just also provide some, material for them to work on, chew on, and become a little bit better. So
what in your so you're doing a lot of experimentation. What's faster, modeling or experiments?
Experiments
are faster.
I think building a better model is way more difficult than doing an experiment. I think I'll debate anybody about that, because I think for me, like, so again, depends on which field you are. If you are building this model for AI or purposes, or like, so there, of course, modeling is way more faster than any behavioral experiment or any neural experiment. Okay. But if we are trying to build a model of the brain, it's like we were discussing about this engineering thing. It's like, okay, I have a problem of like, how is the brain working? But the solutions cannot be anything. It's like constrained by this biological system. So there's like a specific solution that we are trying to look at. And I think aligning the models with that is I can build a model that might solve action perception or action prediction better than the current system, but that might not align with the brain. I think when I said like the modeling is slower, I think it's that bit, which is like having models that are more aligned with brain. Because, like 2012, AlexNet came up, and then now we don't even talk about AlexNet in terms of like computer vision. I think no serious computer vision scientists would say like AlexNet is my model that I start with. But it came to neuroscience and it's still here. We are still using AlexNet. So like, I think things come to neuroscience and they stay for a longer time because it's just very difficult to falsify or like discriminate among these models even. And I think there are maybe for us, there's some of them are like, there's some deeper questions in here as well, maybe, because like when we say we have a model of primate vision, like what do we actually mean? Do we have a model of a specific human or like a specific monkey, or are we modeling the shared variance across humans or monkey, or, are we developing a model of the, all the possibilities, like a superset of vision? Like, so how well should a model of object recognition even predict behavior of one subject or some neuron that I'm recording for in a monkey brain? I think we need to think carefully about those questions, because like, yeah, sure, like the model might predict, one neuron in a monkey's brain at 50% explained variance. But then how well does any other neuron in any other, human brain predict that another human's IT neurons or something? Like, so I think quantifying and sort of setting up the ceilings based on what we actually are modeling. Are we modeling individual human beings or individual monkeys, or, the shared monkey population? I think those questions are sort of important. And then maybe we are done with like predicting core object recognition feed forward responses, because, one monkey predicts another monkey at 50% and there's no way you can improve beyond that or something like. So it's, to me, I think because of these kind of, and of course, as I'm saying it, I'm realizing that like this is basically like it's empirically challenged in some sense. Like that, like, it's like, so it's actually the experiments that have to provide these answers, and we are sort of like limited by technology and how well we can probe the system. So that's why I think slower. Yeah.
Okay. Well, you said ceilings. So the way you've talked about it, it makes me, it's a fuzzy ceiling, I suppose. They're fuzzy ceilings in that respect.
Sure. Yeah.
Yeah. All right. So I'm slowly coming around to the fact that modeling takes a long time. I didn't do any deep learning modeling. I did like a kind of a psychological model. It was very simple, right? And it took a long time, but experiments, I had to go in every day, and it just was, years to publish a single paper.
No, I see where you're coming from, and I totally, that's has been sort of my experience as well. It takes a long time to train a monkey, to implant the arrays and get the data, and maybe, the array doesn't get implanted well, then you have to like implant again. Like, there are multiple problems that can come up. But I just feel like at the end of the day, you have some data, and if you have designed your experiments properly, that's like, especially in neuroscience, which I think is still in the dark ages, like it's sort of like novel data, it's like just, it's anything you do, you can basically, it's novel data and a target for like a model to sort of predict. And I think in that way, it's faster, because like I can build a model like just, put some two convolutional layers together and call it a model. But is that really useful, or is that really taking the field forward? Maybe I answered it too fast about like, experiments are slower.
Yeah, you need to think about that more.
Yeah, I might have to think about it, but I think I'm trying to sort of like tell you a little bit about why I think modeling is actually going to be slower, especially like modeling the brain.
There's physical time, but then there's also heartache time. So maybe those are two orthogonal things, right? So like the other question would be like, where do you experience more heartache and obstacles? And do you think modeling would be the answer to that?
Again, depending on your experiences. So like if I'm like running a monkey, like after I have like brought a monkey to the lab and done an experiment, I have zero energy to do and think about anything else in the day. So it's like I'm done for the day. And I think that way, yes, it's a lot more, at least because that's the experience I have had. I cannot tell how bad it is for like a modeling person or how bad it's like to come up with, like a giant
my code,
mostly I feel like
code.
It's like mostly it's like the libraries are not loading, the version is not correct, blah, blah. So like those are the problems that I usually, face. But at the end of the day, once the model is training, and I don't know. At the end of the day, I feel a modeler is going to be more disappointed because the models don't really predict much more than the previous model. But like the neuroscience experiments, if it's designed properly to begin with, I think it's always going to give more insight.
All right.
Just a biased opinion, maybe.
Yeah, we're all biased, as we know. All right, Ko. So again, correct me if I'm wrong, but the way that I see it, there's this core object recognition story that at the core of it is a feed-forward convolutional neural network. And, you guys in Jim's lab have done a lot to explain neural data. So that's kind of like the basis, the way that I see it. And then from there, you've done a lot of other work. Like you've started adding bells and whistles like recurrence, and you've synthesized images to predict, which neuron is going to be driven by a particular image. So you're making the models more complicated. And I've heard you argue that that what we need is more complicated models, whereas, from a philosophy of science classic perspective, what we like are simple models, right? And because part of the problem with these deep learning models is that we don't exactly know how they're doing what they're doing. And to use a complicated model to explain a complicated organ like the brain, there's pushback on how much that actually buys us in terms of understanding. But you argue that, no, we actually need them more complicated. Why is that?
Yeah, I think it depends on how you define complication, because I think the reason why I might say that we need more complicated models because the models are not really predicting what we set out to predict. So I think making them simpler, I don't know. I don't think that's going to be the answer because the brain is complicated. So anything that is a simulation of the brain will look complicated in some sense. In the other sense, it will not look complicated because if you have correspondences and alignments with the brain, you can point to a part of the model and say, oh, that's V4. And you can say that's V4 in the brain. So that in that way, it might become less complicated over the course of it. It's just a definition of what complication and what is interpretability and what is understanding. I think those, and because there is no objective definition of those things, I think these kind of conversations usually, lead nowhere. I'm trying to think of this thing, for example, when I was in my graduate studies and during my PhD, we had models of motion after effect. And if I spoke to anyone at VSS or SFN or cosine about these models, everybody would say oh, this is completely understandable, interpretable, simple models that we have intuitions about, which is okay, you show coherent, so you show a random motion pattern and you have these motion detectors, they're all firing and they're all firing equally. There is no basically if you show a stimulus that is moving upward, the upward neurons will do something and it's going to be some response, which is going to be higher, compared to the rest of the group. If you are only showing upward motion for a long time, those are the neurons that are going to fire and get fatigued. And then when you show a random pattern, you'll see everything else is firing higher and the upward motion detectors are kind of firing a slightly lower. So overall you will have, bias towards saying, okay, it's going, maybe the motion is going downwards, something like that. And this can be modeled, and people have modeled this and I think those models compared to artificial neural networks now, they might be considered, simpler, more intuitive, understandable models, less complicated. Now I'm thinking let's go to 5000 BC. People are talking Tamil or Sanskrit or Greek or some other language, trying to explain, I'm time traveling back then, trying to explain the motion adaptation model to them. They'll be go away. What are you talking about? This is not, I don't understand anything. So how these models are not real models of the brain. I don't know. And I think I feel the same thing is happening now, which is artificial neural net, but remember the motion model that I just mentioned was predicting this adaptation phenomena, this behavior. So that was kind of the goal of this modeling. And it had some relevance with how people have looked at the brain and neurons and so. But if I tell this in 5000 BC, people will be I don't know, this is not mapping into our worldview. And I think the same thing might happen right now with convolutional neural networks and some terminologies and things like that. It's okay, this is too complicated, this math, I cannot fit into my low dimensional kind of behavioral space of how this high dimensional areas are functioning or responding. So I don't take that complaint seriously because I think with more familiarity with these terms and models, that complaint is just going to go away. As the models become more and more powerful in predicting different behaviors, and we will see, for example, use of having these models in sort of real world applications. And I think that kind of fear of, oh, this is a too complicated of a system is just going to go away. And for those for whom this won't go away, they'll just probably have to live with it.
Yeah. Okay.
But maybe the more I think one of the reasons why I feel people like simpler models, it allows them to like maybe think through like if the model gets stuck, what to do to improve it. And I think that to me is like a real value of having a simpler, more interpretable model. And there, it's a question of efficiency. If you can have a complicated model kind of self-correct itself or self-improve itself, which is kind of a future goal maybe, that might just be a more efficient way of dealing with this problem than kind of like humans kind of coming up with their own intuitions of like what is a better model and things like that. And I think we were discussing about this engineering background. To me, that might be something I'm more prone to accepting because of my engineering background, because I just feel like there's a question and there's a solution, and these are just tools to get to the solution. Doesn't matter if I intuitively kind of understand it or not. As long as it's aligned with the brain data and things like that, it's fine with me.
So I actually got even more excited to talk to you because after we had set up this episode, someone in my course asked, because in my course I talk a lot about, I use Jim's work and your work to talk about convolutional neural networks and how it relates to the ventral visual stream. And then someone in the course asked, what about the dorsal stream? Because I talk about the two visual streams.
Right.
And this goes back to the question of like what it means to understand vision. And I know that one of the things that you're doing, so the question was like, why aren't there models for the dorsal stream as well? Why is it all ventral stream? And I know that you are starting to incorporate, and you have some background with the dorsal stream as well. And maybe we should talk about what the dorsal stream is, just to bring everyone up to speed. But so are you just starting to incorporate other brain areas now? What is your yeah?
Well, the first thing is that maybe if that student is interested in doing a PhD or a postdoc, send them my way, because that's the kind of question I was also asking about. Like, okay, what is the dorsal stream doing? Because I had spent like 5-6 years studying the dorsal stream, which is slightly sits above the ventral stream in sort of anatomical location in the brain.
Let's say what the dorsal stream is, like what it classically is. Do you want to say it, or I'm happy to as well.
You can say it.
Okay. So classically there are two visual streams. It hits V1 and then it kind of branches off into a ventral stream, which is what the massive amounts of Neuro AI and core object recognition is about, where it gets processed over hierarchical areas up through V2, V4, IT, until we suddenly have neurons that respond to whole objects. But the dorsal stream is classically the where or how stream, which is much more related to the motion and spatial aspects and our actions, right? So it's activity related to, and that's where I spent my career, is basically from more or less in the dorsal stream. Yeah. So I don't know. Did I explain that okay?
Yeah, absolutely. I'm usually now, like, I think I'm usually very careful about assigning some behavioral function to areas.
Yes.
I mean, mostly I start talking about anatomical locations, and like, who knows, like, you might find that, dorsal stream is just big part of core object recognition.
Right. Well, I mean, so the thing that has been, I guess, always known, but not paid so much attention to, is that there's a lot of crosstalk between the dorsal and the ventral stream, but we've kind of studied them in isolation, right, as two individual separate things. Yeah,
I mean, I think that's a sort of, I see that as an opportunity to sort of like really take this sort of studies forward and like trying to incorporate looking at dorsal stream as well. Just one point I wanted to make is that I think there are folks who are beginning to build models of the dorsal stream in the same way as, the ventral stream modeling has gone. I think I recently saw a paper from Chris Pack's group, and I'm sorry if I'm forgetting other authors. I think Blake Richard was part of it. Patrick was part. Like there's I think it's in bioRxiv at least. There's work done from Brian Tripp's group trying to model these systems. Like, of course, like dorsal stream has a lot of modeling, prior modeling work that is not kind of similar to the convolutional neural network stuff. But I think people are beginning to build them, and there are different objectives that they're proposing as like sort of normative framework for like how the dorsal stream gets sort of trained up. Like, I think those are nice hypotheses, and we'll see like whether the data actually, supports those, models or stuff like that. But I think for me, sort of trying to get into this area, those are really nice work because like that gives me some baseline ideas or baseline models to start testing and probing. When I start designing my experiments, I think those models will really help me to sort of make a good experimental design.
But are you building? So I actually don't know like what kind of model, because it wouldn't be just the same. You wouldn't just use a convolutional neural network to model the dorsal stream, right? And so are you building models yourself also, or are you going to incorporate?
I have not personally built any models right now. I've just been testing some of the models. So I started testing some of the models that were like mostly used for action perception or action recognition models. They have these like temporal filters, like they're still convolutional. It's just like more dimensions to the convolution. It's like a time dimension. So I think those are like good starting points because like they're easy to build maybe because they can use the same kind of like training procedure. But I think we have to at some point become a little bit, be okay with being a little bit, go lower in terms of prediction because we need to move from static kind of domain to a dynamic domain. And I think my usual experience has been that whenever you make this jump, like all these models start to kind of like not perform as well, not predict the neural responses as well. And so I think to me, like that might be one of the reasons why maybe some people are building these models and they're not really coming out because they don't really predict anything. Like, so maybe backing up a little bit, like my main sort of interest in this dorsal ventral interaction question kind of started when I was mostly recording, showing static images to the monkeys and recording their responses in IT. And these are, objects that are either like natural photographs or, some kind of synthesized images. And I started thinking about my previous work in dorsal stream, and it was like about motion and, there were dots moving and gratings moving. But if I think about the real world, like I never see dots moving or gratings moving in the real world. Like there's objects are moving. And to me, like if I have to have any real world relevance of my current research, I just felt like, it's a dynamic world. I'm moving my eyes and I'm moving myself and the objects are moving. And if I think of these questions or think of these behaviors, dorsal stream kind of pops up in any literature search that I do. It's like self motion, motion of objects or motion of like, not objects, but like maybe motion of like something in my visual field. But then I was wondering like, IT has this nice representation of what the object is. And if the object starts to move, is it does all of it fall apart? Like what happens? Like, so just out of curiosity, I just started recording from these neurons and when the objects were actually moving. And then I started kind of, this work has not been published, but it's like the sort of the preliminary result is that, well, IT kind of can predict where the object is headed, where it is moving. It's not, we know from previous studies from Jim's lab that from looking at IT representations, you can tell where an object is.
Right.
This was from Ha Hong and Dan, 2016. Where the object is located, you can tell in a static image. So there's one trivial solution where, okay, like if you can tell where the object is located at different time bins, you can maybe combine that information to tell where the object is headed or where the object is going. What I started finding is that like, it's not only that, it's like you can just take a snapshot of like maybe after you have started this movie, 200 milliseconds, 300 milliseconds later, you can just look a small time bin and you can tell where the object has been going. So it's like there's a predictive signal of where the objects are headed. So that sort of like, then I started thinking like maybe this is coming from the dorsal stream or is it, but again, these are again, like ways of thinking that I've kind of discarded in the last few years. So I feel like the way to think about this is like, can a vanilla ventral stream model explain this neural responses already? Then not to invoke dorsal stream at all. Maybe they will fail and then the dorsal stream models are actually necessary to, account for this neural responses and also the behaviors that I can test based on these kind of stimuli. So that has sort of been my approach. And the dorsal and the quick update on the ventral stream results is that these models, they're not really predictive of these kind of responses at all to some degree. So that gives me hope. So, yeah.
It's always good to have hope when you're starting your career. Although not that you're starting your career, but your new start.
Yeah, exactly.
But you said you've discarded thinking about it in that way from like different brain areas. Is that because you've discarded thinking about assigning roles to individual brain areas or? Yeah,
sure. Okay. Yeah, absolutely. I mean, that whole way of thinking is like, I think it's primitive. It's not going to lead to, the brain is doing what it is to like make us go through the day, and like all areas are coming together in some form or the other. And so I think it's, I don't want to come up with the answer that like dorsal is doing blah, blah. Like, I think it's just part of a system that is trying to solve a behavior. And the answer is going to be, here is a model that has elements in it that are corresponding to neurons in the dorsal stream. And together they, solve a behavior. Now you can ask the question, if I really want to satisfy someone, like what is the dorsal stream doing? You can start doing perturbation experiments in the model or in the brain and say like, what happens to the behavior if I take out, part of the dorsal stream or part of this and that. But then I'm mostly worried, like, what is the answer going to, like, my answer is going to be like, oh, it takes a 10% hit for video A versus video C. Like, I feel like those are the kind of answers that are really going to come out. But people are going to, I might spin this off as like, oh, but this is about, function X, or like it's about something about predictive coding, or I can give the answer in that form. But I think at the end of the day, it's just going to be a big lookup table of like, you perturb this part of the dorsal stream, you get X hit on this particular behavior, this particular video. So that's why I feel like my answers need to be in the modeling kind of framework.
Yeah. Words. We're limited by our language. It turns out this very special thing that we have, language, also is very limiting in some respects, I suppose.
Yeah, but I think if the models can relate back to the language, I think then some of the, problem or the tension might be relieved a little bit. Because I think now so for example, this is maybe slightly off topic from the dorsal ventral discussion, but like if you look at a model of ventral stream, like you can look at brain score and like say, okay, ResNet 101 or something has some numbers associated, like some scores. I can see why people have a problem with that model and why people say this is not interpretable, because like there are parts of the model that are just don't know what it is. Like, how does it map to the brain? Like, I can call like some part as IT or some part. There's 1,000 different things in between that I have no clue of what they are. And like, maybe the model is not performing because of those, computations that are happening in those layers. How do I relate this back to the brain or something? So I feel like that is a real problem. And I think it is in our interest to start coming up with commitments to different parts of the model and then falsifying them based on those commitments. So like an interpretable model should be like, if I write so what is the interpretable thing in neuroscience? Like a paper, like the abstract of the paper should be at least interpretable to anybody.
Yeah.
So if a model has components to it that can talk to each part of that abstract, like, you have a task, you have a neuron, you say something, and if you can basically map your abstract to parts of the model, and if the model can map onto the parts of the abstract clearly, that I think just gives the model interpretability. And I think that level of crosstalk and language, I think, should exist. And I think that language I'm, trying to sort of develop myself to, even when I'm thinking about modeling and experiments.
Well, after all that about how we shouldn't assign roles to individual brain areas, you are doing some inactivation experiments, right? So what's going on there? Why are you inactivating individual brain areas?
Yeah, so I think that's basically try to so there are a couple of studies that I think at least I've done recently. One has been already published, which is like inactivating ventrolateral PFC and looking at core object recognition behavior, and also looking at representations in IT when the monkey was doing that task. And the goal was to basically expand or test whether these feedback loops that are existing between these areas, are they actually playing a role in that specific behavior that we are, studying? Because the current models are incomplete and they're not predicting enough. So like it's kind of makes sense that maybe there are other areas and there are other connections that are, important. So that is not to say like PFC does X, right? It's like
it does everything apparently.
Yeah, I'm sure it does a lot of things. It's just like for me to actually ground this problem, it was more like what kind of role or what kind of signals do I, at least from the inactivation, it was like what kind of signals go missing in IT when I inactivate them, inactivate PFC, and what kind of sort of deficits do I see in behavior? And then the data, again, as I was saying, is not like, oh, you cannot identify objects in an occluded scene or something. It's not an answer like that. It's mostly like here is a big data set. It's like, it's not satisfactory to many people. Like, here's a giant data set. It's clearly, like you see, like there's an average effect, PFC, no PFC. Okay, I've shown you this. There's a prediction that is coming out of a model that is like, this model is a feed-forward model. It might not be doing XYZ, and voila, those are the images where these effects are also much more concentrated on. So there's a story there. It's like, okay, it's clearly part of a system that is not the feed-forward system, that is like maybe going beyond the current feed-forward system. But like, at the end of the day, I think the next step is to build a model that has a unit or module that is called, VLPFC, and perturbing that should produce the same kind of deficits. It's like and this is where I think it's a very hard thing to do. It's actually easier thing for me to like perturb PFC and like get this data and say like, okay, this area is involved, but to then build this model, I think that's going to be really difficult. And I think, and there are limitations to perturbation data, for example. I think, and this might be like relevant to the conversation about perturbation experiments. Because I think even after this perturbation experiment, I think actually recording in that specific area with the same kind of task and same kind of stimuli might be more constraining for the next generation of models. And that is exactly what I'm doing currently. But at the same time, I was thinking like what kind of perturbation experiments might be like, may have more benefit for the kind of models that we have right now. And that kind of led me to developing, mostly we say developing a lot, but it's like basically testing this sort of chemogenetic strategies where you inject a virus in a brain area, and in my case, I also implanted a UTA array on top of it. So we injected dreads in V4 that was supposed to be like, silencing or down-regulating the activity in V4, and then we implant a UTA.
Sorry, can you say what dreads are? Because we haven't. I don't think I think we've mentioned them on the podcast before. But what are dreads? And then I also want to ask you. So you injected, and then you. In a separate surgery, then you implanted?
No, it was done on the same day. It was done on the same exact surgery.
Okay. Sorry to interrupt you. Yeah.
No problem. So the basic, I think, idea is that you inject a virus that ends up sort of manifesting as a receptor in a neuron that you can activate or deactivate with various means. It's the same idea with optogenetics, the same idea with chemogenetics. Mm-hmm. In the optogenetics, to sort of activate or, that particular receptor, you need to shine light on that neuron,
right.
On that area. For chemogenetic, you need to basically inject a drug into the system. And, so there are some pros and cons of these two different or multiple different things. So for example, you're kind of like limited in terms of where you might want to inject for opto because, light delivery is tricky because you have to be mainly maybe, restricted to the surface of the brain. Deeper structures might be very difficult to target at scale. Maybe you can target like one or two neurons. In chemogenetic, you can basically inject the virus anywhere you want in the brain, and it kind of gets activated through this sort of like injection that you do in the bloodstream. So it basically activates or tries to activate all these receptors that has been, produced. But then there's like temporal limitations. So opto can like go very fast, quick on off. But the dreads are more like mucimol in some sense. Like it's on, the effect is on for some time, and they're usually weaker.
A week?
In my calculation, no, weaker. Not
weaker.
That would not be so good. I think it's so from my estimates, I think it's mostly on for like maybe a couple of hours and sort of goes away. It's like very similar.
Mucimol.
At least the main time is like mucimol. So, and what I've been doing is like we have these arrays that you can actually test, you can show the same images over and over again after you have injected the activator drug, and you can sort of see how quickly or what is the kind of time course of neurons responding lower or higher. And then you can have behavior on top of it, like the monkey is also behaving on different blocks. So you can kind of see like, there are some deficits that are coming up, and then the deficits sort of like go away at the end of the day or something. So I think I'm at least thinking of like, how do I take this and like make it useful for models? Like, okay, I can say like a V4 is involved in, object recognition. That's sure. Like, I don't know. not too many people will be interested to listen to hear this anymore. But if you give me like, okay, BrainScore has like 1,000 models that all have like 0.5 correlation for V4 activity. But now I give you some V4 inactivation data, and then 900 of them fall off, and they cannot really predict the kind of, pattern of deficits that V4 has. That might be as, important than tool, or maybe an important problem. But as you see, like here, you need to have a model that has like a brain tissue mapping of V4, and, where are you injecting the
right
virus in the model versus in the actual brain. So, I mean, there are parts of this problem that are still more complicated, but I think the chemogenetic strategy, at least for areas like V4, where you're injecting, and these are mostly retinotopic areas. So there is some level of, a correspondence in the models. And then you have a neural data on that. So you can actually just say like, I don't care about like your assumptions, just like fit to the neural data.
Mm-hmm.
You have V4 neural data with and without activation. You have, your model with and without activation, just fit to all the data that you have got, and then predict what happens to IT or predict what happens to behavior in the model. And that's how you validate the model. I think that's a stronger form of using sort of this perturbation experiments, because I think it's not uncommon to see, experiments where someone says, this area I perturbed, did nothing happen. And someone says like, no, you didn't do this, blah, blah, blah. So it's like, right. If the answers are always yes and no, I think it will just stay there. It has to be sort of falsification of like competing models, and then maybe some data will be more useful than the others. The other, I think, upshot of having something like this is that imagine you have monkeys that are doing these tasks in their home cages. Like we have a lot of monkeys that are trained up, and they do these tasks all day in their home cages whenever they want, because they have a tablet, they can do these tasks.
Yep.
You can pair this up with that system, and you just need one person to just go and inject like something in a monkey. And then basically you have days where you can like, run this with some part of their brain, quote unquote, deactivated. And you can multiplex even with the viruses. You can like, target inhibitory neurons, excitatory neurons. You can have different viruses injected in different parts of the brain that have their own corresponding activator drugs. So that I think there's a lot of kind of interesting data sets that can come out of this approach, which should bear on the modeling questions.
How much of your future, what I want to know is like the vision that you have for your own lab, and how much of it is going to be this kind of work, and how much of it is going to be modeling and so on?
I think a lot of this is going to be this kind of work, and like just pushing the boundaries of experimental neuroscience. I think the modeling is like, it's like that's going to be the backbone of the lab. Like the computational part is like no answers can be provided from the lab if there is no model attached to it.
Mm-hmm.
So I will be collaborating with others. I'll have people, working with people in the lab who will be building probably these models as well and testing them out. But I think that I don't think I will be, happy at the end of my career if like I did not improve like a model or something of the system even after doing all these different experiments. So it's going to be a mix of that. I mean, maybe, I don't know. I mean, I should probably mention this. Like, I'm not really interested in building the best model for core object recognition or dynamic visual perception or visual cognition, just for the sake of building that model and understanding how the brain works. I mean, I don't quite motivate myself that way. I think, and it's kind of interesting because like, I think for training purposes, these were the most concrete fields and most concrete labs that I thought, okay, this is where I should get trained. But I think I kind of wake up every day to sort of think that maybe my research is going to help someone's life. And I think this is kind of like, oh, wow, what a great person you are. But like, I think I'm going to tell you like a small story. Maybe this is,
please,
you can cut it out if it's not relevant. So I've been working in visual neuroscience, and people know that I work in visual neuroscience back home in India. And
what do you mean people know? Like India knows?
Like
your
my
family?
My family. Sorry, people. 1 billion people know me. No, like 5 people. 1 billion people know that.
That's more than know what I do. So there you go.
Okay. Yeah. So among those 5 people, or maybe like 10, Indian families tend to be bigger. So among those 50 people, then there are some of them that I think they have some idea of like what I might be doing, which is completely wrong. And I think I had this encounter with someone, and unfortunately their kid, got diagnosed, to be in the autism, spectrum. And so I was meeting them, and they asked me, like, oh, so what are you working on these days? And I'm like, okay, I'm working on visual cognition. I'm saying stuff like, how do we reason and things like that. And, this person turns to their kid and tells them that, like, your elder brother will one day, like, is working towards these solutions. And like, and this kid is like very young, can't understand anything of what they're saying, but they were basically telling them that like, he's going to come up with the solution that will cure you.
Right.
And it just felt like I just was feeling like I was thinking like I'm never gonna do that. I'm failing. I mean, I cannot find any connection to like, what this translates to. And at that really, I mean, that was kind of a pivotal, like a point where I started thinking like I need to find real connections with what I'm doing and how that really impacts or translates. Not just this, like the first paragraph of a grant saying like, I'm working in dyslexia, or like if this is relevant to like blah, blah. It's
schizophrenia.
Like really trying to, schizophrenia, exactly. So really trying to find, and then I started actually, I mean, that's going to be at least some part of my future research is like trying to find out how, having these models that are these concrete models with brain maps, how are they beneficial to diagnosis and potentially treatment strategies in some of these neurological disorders. And I've started working a little bit towards these goals, and I'm very excited about this because I think there are real benefits. And I think you were mentioning about this like neural control studies, and I think those are the kind of studies that are really sort of giving me hope that like there is a way to like contribute to this part.
That's
of
like
my desire list.
That's kind of a magical thing. So that wasn't your motivator for a long part of your career, but from a place of guilt. But it's developed into
guilt is a great motivator.
Guilt is a great motivator, but it's developed into like a real motivation for you. But I never had that. I don't care about helping people, and so I always felt bad writing schizophrenia in a grant, for example, right?
Yeah, I mean, it's a little bit philosophical. Like I don't even know. I cared about helping people in some way. Like maybe I'm basically thinking I'm trying to help people, but I'm just trying to help myself. Maybe thinking like, oh, what if I have Alzheimer's or something in my old age? But like, but I think currently at least I do feel like that gives me some level of satisfaction to think that there is potentially some link of my research that might be getting help to for someone.
Yeah.
I think.
I mean, it is interesting to think how through our work, through your work, through people's work, your interests change, and as you develop and as you ask different questions and answer different questions, it's just kind of a magical thing. So that's thanks for telling that story.
Yeah, I think that definitely like impacted me a lot. So, but I'm also like I think these are related issues. Like I think like you were asking about understanding and progress and like things are like understanding vision and visual cognition. I think the moment we start to like measure our understanding like in the brain score way or something like, then I think these answers to like the clinical translation becomes more concrete, maybe like, so I think they're very related. It's just for me, it took me a little bit to like figure out, and maybe I'm still working on it, like to figure out where exactly are the most relevant parts of it. And I think my interaction with a lot of folks, who are doing autism research, like really helped. So for example, I've been in touch with, Ralph Eros at Caltech, and we are sort of collaborating on a project. And I think like those discussions and like reading the papers, like really, I think they have a lot to contribute to what I do. And I think our way of thinking about the system has a lot to contribute to that research.
Interesting. So, you mentioned the image synthesis work a little bit. Yeah. Can we talk briefly about that? Because maybe you can just describe what the work is. I talked with Jim about this when he was on the podcast, but we can kind of recap because it was kind of splashy, right? I kind of want to hear your thoughts on how you currently think about that work as well.
Yeah, so this work was done in collaboration with Pooya Bashivan, who's at McGill now. And so me, Pooya, and Jim were basically, we did the study together. And so the basic idea was that we were recording in V4, and we have models of V4 neuron. And the question was that, can you, from the model, come up with stimuli, using the model, can you come up with stimuli that puts the neuron in specific desired states? And one of the states that we considered was like, let's make it fire the most we can. So the model will tell me, sorry, go ahead.
So this is the control aspect of understanding.
Yeah, exactly. So that is like, prediction and control. And this is the control part. So the models could predict, but maybe they couldn't control because maybe the images that were synthesized. I mean, there's a part where there's a separate technique, which is how are you synthesizing the images? And maybe there are ways in which that doesn't need to be attached to the model. That specific model that you're using to predict, that they can be two separate things. But again, like for us, it was like, we were using the same model to come up with the images as well. So we came up with the images. We're trying to control the neuron, and we were targeting like, okay, V4, let's make this neuron fire as high as possible. That was one of the goals. The other goal was, let's take a bunch of V4 neurons that kind of share the same receptive field, properties, and try to set one of them to very high and the others to be very low. This is like a population level, control. So these were the two goals that at least we thought, let's start here. And then we were asking like, okay, this question seems like, you have heard of this before, because like, what does V4 neurons do? Like they respond to curvatures. What does V1 neurons do? They're like Gabors and orientation, and V2 is like texture, and like IT is faces. Like, now you come up with the stimuli and you look at them and like, I don't know what to call them. Like maybe they're something. But then for us, we kind of like ignored that problem. We just said like, okay, let's just take these images and like see whether the model's prediction is right. Because then that at least should show that like using these models, you can control the neurons to some degree. And that was basically the study. We had some success, and we were comparing our, success rates with like, taking a random sample of images, or using the previous sort of thoughts on what are the stimuli space that excites these neurons, like curvatures from. Yeah.
I want to hammer this home because the images that drove the neurons were, and you mentioned this, but I just want to reiterate that they were terribly unnatural, right? They're not something that you would see. Well, I mean, there are elements that you would see in nature, right? But the majority of them, weren't they just something that you wouldn't make sense of?
Those were like, I don't know what even called. I mean, there's some pixel, conglomerations. Like, so there were two studies that came out on the same day, and I think the other images are even more scary. So this work from Carlos Ponce and Marge Livingston, Gabriel Kreiman, Will Shaw. So they were trying to control IT, or they were trying to like, come up with the images for IT. Those images look even more scarier than, like because they have some kind of natural relevance. They look like out of a horror movie or something. But like the V4 images were more like texturey kind of images. And we are also restricting ourselves to like, black and white images and things like that. So I think that was part of it was constrained in certain ways that led to those images. But as you were saying that, it did get a lot of attention, but I think some folks have gotten excited about the wrong thing from the paper. And the resulting images that drove V4, I think, cannot be the protagonist of the story. Because I think that kind of became the story, because like we like to say like faces excite IT neurons, or XYZ excites XYZ areas. And I think in that formulation, then it became about the images as sort of our new understanding of the system. Whereas that was not about the images. It was about, look what you can do with this model, because this is the model that tells you that what is going to be the predicted neural response for any given image. So I think that's where we are in the sense that we think of this as a stronger test of the model, because there are many models then that can come up with different images, then you can test those as well. And I think there's very, very interesting work from Nico Krieger-Scotter's lab about controversial stimuli. I think those are the right kind of approaches, at least to me. Like you pit these neural networks against each other and then synthesize stimuli and then test them. It's a different kind of control experiment, but at the end, it's basically about model separation and finding the best model. It's not about looking at those images and making stories about them.
Yeah.
The other side of this story, though, is that this should not make someone feel like, oh, solved. Core object recognition, this is the model.
Wow.
Clearly they have, so, yeah, I mean, that's the other thing I feel like, there's ways of presenting data that can prove our point. It's a proof of concept study to me still. It's like, look, like if you take this approach versus the other approach, this approach, like our approach is better or something. Like that's kind of the way to present the study, but that doesn't mean that our approach is like the best approach or like we are done. So
do you have people suggesting that we're done? Do people?
I don't think we have people who would explicitly suggest that we are done, but they might use this as an example of like, look how great the CNNs are. And I think it depends on whom you're talking to, because I can also use the same example to kind of like talk to somebody who's just basically saying, oh, CNNs have adversarial images and this is like a completely wrong domain of like models. I can then use this example to say like, look, you can do some useful stuff. But if I am coming up with things like, you need recurrence and you need other areas to incorporate, someone might go like, but you can control reasonably well. Like, why do you need to like incorporate all like, so if you really look into the models, look at the generalization of the models, it's not that good. It's like, again, not that is a very arbitrary like word usage, but it's like,
But you feel like, in some sense, you're your own worst critic, right? Because you see all of the nuts and bolts and you see what's missing and what needs to happen. And so do you feel like people are too complimentary, are too impressed with the current work? Because I think
they should be.
Well, yeah, they should be.
I think they should be, but I think they should also, like everything else, they should just, I actually think this is our responsibility. To sort of also expose where if you read the two papers together, like the neural control paper and the recurrence paper, they're basically, one paper is sort of highlighting how you can use them. The other paper is sort of highlighting like, here are the images that humans and monkeys are good and the models are failing. So these are the ways to improve it. So I think if you take all of these studies together, then you might get a more balanced perspective. And I think my goal, at least, sometimes for a lot of reasons, you know better that like you need to sell the studies in a certain way. But I think in these kind of discussions or like in papers, in the discussion sections, like we should always be highlighting sort of the confounds or the potential, places to improve these models. Even for core object recognition, these models fail in very trivial ways that are maybe some people who are just reading this paper might feel like, oh, that's probably already solved.
Yeah.
Maybe they don't exist. Maybe this is a thing that I've created in my head.
More guilt, more,
yeah, actually.
So I know that one of the things that you're interested in is visual reasoning, right? And I don't know if you want to explain why you're interested in it and what it is, but one of the ongoing criticism. So non-human primates is kind of like the gold standard, right, in neurophysiology, and you need an N of 2. You need 2 monkeys to publish, classically. But and recently there have been a lot of people working more and more in rodents and mice, and of course there's always been the disconnect between mouse brain and human brain. And one of the reasons why people like to study non-human primates is because it's like the closest thing that we can study that resembles human brains. Do you see limits to studying non-human primates to get at our intelligence? So the reason why I asked you about the visual reasoning is because you're starting to ask. So object recognition is a fairly simple thing, right? I know it's not simple, but it's we recognize objects. But now you're starting to ask more higher cognitive, quote unquote, questions. And I'm wondering if you see limits to using non-human primates for that.
Yeah, I think the answer will be sort of, my answer to that question will be maybe based on the kind of data that I will be collecting in some sense. So the way I see this problem is that ultimately, at least for myself, I'm not suggesting that everybody has this approach, but I'm pretty human-centric in my worldview. And I think my goal is to find out how humans solve a particular problem. So they are basically like the main model that I'm interested in. So I think we start from human behavior on different tasks, and ideally we'll have a model which is like currently maybe, some form of a convolutional neural network, which has many areas other than ventral stream, like dorsal stream, PFC, and they will be kind of like predicting parts of the behavior of the humans and maybe at full capacity or something. And I think at least one angle of approaching the monkey research would be like, can I get some neural data that might be constraining for those models, might improve those models, and usually, I mean, the way people go about it is that they collect some neural data, come up with an inference that is more, can be like summarized as like a very smaller kind of principle, like have recurrence or like a smaller model. And then they incorporate that idea into the bigger model and ask like, did I improve my model, my bigger model? I can do that. I mean, I'm probably going to do a bit of that, basically like saying, it looks like this other areas in the monkey brain is associated with this particular behavior. And maybe that is going to improve my development of the models. The other thing could be like you just directly, feed the data that you're collecting into the model building itself. So you're getting a lot of monkey data. So then it's a matter of like questions of like how much data is enough data. And I think we are getting more and more data. So I think this is the right time to like start putting them in the models. Like, so right now I'm involved in a project where all the data that I've collected is getting kind of filtered into the training part of the model, and the models are being regularized with that data essentially. So like, and those models are becoming better predictors of core object recognition. So like, that is one way of bringing in the monkey neural data and the monkey behavior maybe to this problem. The other way I think about this is that maybe, humans and monkeys share a very, I mean, it's not maybe, it's probably proven in many ways that we share a very similar visual system. So even if I just get responses of the visual neurons in IT or other areas during showing some of these movies or some of these videos on which the task is based off, I can be providing constraining data for the model of like, you need to be in this representational space and then solve a problem. So like, it's a two-part kind of approach where the neural data is basically constraining the representational space of the model. And then on top of that, you add a decoding layer that is like reading those representation, and you can have multiple ways of decoding the task. And then you ask like, which one, or you can then compare it to human behavior. And I think this could sound novel or surprising, but like this is exactly the thing that Jim's lab, like our lab has been doing for core object recognition for quite a while, where we were recording in monkey brain, but then comparing the decoding models output to human behavior. I have now started working, like, because I was also getting the behavioral data from monkeys, I have started now looking at trial by trial and like image by image behavioral correspondences with monkey neurons and, monkey behavior. But it was basically monkey neuron human behavior. We had a paper with Rishi Rajalingam looking at monkey neural responses to like words and non-words and their correspondence to human behavior on those sort of orthographic processing tasks. So I think there's a way to like do this kind of separated from a behavioral task. Because I think maybe if you're asking that does the monkey need to do the behavior for them to be relevant to this task? And I think the same applies to rodents and other species. It's just, to me, ultimately, again, as I was saying continuously throughout this, discussion, is that at the end there is a model, and whatever you do, you need to kind of show that adds to improvement of the model on something. And now from just what we're talking about, I can say like, maybe my goal is like not to improve like prediction on human behavior to ceiling, but maybe it's like if I'm doing maybe predicting behavior of neurotypical subjects versus, people with autism, do I have some traction on that problem? Maybe like I can do, like inhibitory excitatory imbalances. I can create them more easily with chemogenetic perturbation in a monkey and then test what those representational spaces are. And those could be like kind of constraining ideas for when you're building models of people with autism. So I think there are many, many ways in which, and I'm saying all of these ideas and with the risk of sounding like a scatterbrained person, like has 2 minutes. But I think at the end of the day, I think these are the things that excite me. So I think, and I won't be able to solve it all by myself. So I am hoping that a lot of people who are kind of maybe similar minded, we all come together and kind of try and tackle this problem.
So Neuro AI. A lot of your, at least, most recent career has been using deep learning models to shed light on brains. So this is the arrow from AI to neuroscience. Do you see, and part of what you're doing also is using brain architecture and neuroscience, some details to improve the models bit by bit, like you were discussing. Do you see neuroscience helping AI, or does AI not need neuroscience? Can AI just scale up and go to AGI or what?
That's a interesting question. And also, I think I'm probably not my answer might not be that satisfactory just because of my lack of knowledge in a lot of these domains. But I think of this problem in different ways. So like, if I think of this as like, okay, I'm going to build a calculator, and should I constrain myself with the brain data? No, it's going to be like a terrible calculator, for scientific computing or something. So like, if that's the goal of an intelligent system, is like to compute, calculate things fast, and like, then I think constraining it with neuroscientific ideas and data is like a bad idea. Now, if maybe we can make a distinction of like behavioral data and actual neural data. So if I want to prioritize in my head, like which data might be more informative to building models for AI, I think behavioral data will come first before neural data. Some of the examples might be like moral machines, kind of data that is part of the MIT Media Lab. Like, I think if we are trying to constrain a system to work like humans, then human behavioral data, I think, will be key to constrain this.
I mean, that's kind of been the success of deep learning, right? Is because the old way in neuroscience was to build a model out of kind of intuition, and then compare it to data. And the new deep learning approach is to build a model and train it to optimize it for a task, like an animal or organism would perform. And so it's all about behavior. And lo and behold, the model predicts neural data well also, right?
Yeah. Yeah, definitely. But I was maybe making a slight distinction between like overall performance in a behavior versus like following the pattern of human behavior, the error pattern. So like ImageNet trained models are trying to get the labels correct, which is a behavior, but like humans might not always get those labels correct, and like they might have different patterns. So I think I was mostly thinking like this error pattern of like what kind of decision do we make given some kind of confusing stimuli or things like that. Those kind of data might be more relevant to models if they want to sort of operate in a human regime, because I'm thinking of like a system that might be like, helping somebody go through life who are unable to do things in their life. Like that machine or robot has to interact with the person. And then I think might be important for that system to be constrained with human behavior to some degree. For those purposes, I think behavioral data is very valuable. At least that's how I think about it. For example, also AI in healthcare might be something that might be very constrained. And there, I think maybe the neural data might have some bearing.
Really?
On that. I mean, it still has to be shown, I think.
Yeah.
But I feel like there might be some, as I was saying, that this ideas of like, how does the brain, differ in a neurotypical subject versus an atypical subject, it just depends on the scale of the data and how we are getting it. That's the relationship of the brain representation to behavior. I think those kind of data might help us to build better models of the atypical systems, and then use solutions that might be catered to the atypical system. Now I'm kind of, being very abstract by me. I can come up with like a dream sort of example where if you know exactly how like a system is learning, for example, a new task, and you can do that for both atypical and neurotypical populations, you might be able to use the atypical model to kind of come up with a learning sequence that produces neurotypical behavior, even though it's an atypical system. So I think that is definitely within, I think, the genre of like AI healthcare kind of like approaches. So I think that way neuro to AI links probably are more clear to me. I think generative models might have a boost if they're regularized with neural system data. That is another maybe angle. But yeah, but it's so I would just not. What I'm mostly worried is that it's not like, it's just not obvious that if you have some brain inspiration or like neural data is going to improve AI models, right? That's what I'm kind of maybe pushing back against. It's like maybe you can get behavioral data and that's enough, and you don't need to poke around.
But isn't it interesting that, these deep learning neural networks are based on 70, 80-year-old neuroscience, like fundamentally the idea of a neural network back with even the logical units. I mean, and you're adding more biological constraints to your models. So it's an interesting
well, that's too, I mean, I'm thinking of that, like, so the first part I agree that's like, that's where all of these ideas might have come up. And that's a good reason to keep, looking at neuroscience for, inspiration for building better models. But if I look at the last 10 years, I really don't see a concrete example of like, you read a paper in Nature Neuroscience or Journal Neuroscience and took that idea and implemented in a model that is being used by, at the end, they're like engineering hacks. Like, I mean, both groups like to use it as PR, which is, I think, the reason why so it's great for that purpose. But I think in reality, at the end, you can have an idea. I mean, and that's fine to me. Like, it's like, even if you have an idea of a dropout and then you figure out how to really like tweak it to make it part of a model that does something, that's great. And I think in that way, it's really good to have neuroscience as a inspirational kind of umbrella on top of everything. Good for my career, because then I'll be able to talk to those. But I think, I definitely think there is purpose of neuro. I mean, there will be use of neuroscience for AI, but we need to be careful to not oversell it, maybe. And maybe we should, I don't know. But I think it's the other way around for me makes more, to me, it's more valuable. Especially because I think, you're trying to measure data in the brain that is noisy. This is like sample limited, and then build theories and models around that, like what to expect, like how to think about high dimensional spaces, blah, blah. So like, to me, like once you have a model that is doing a very, high level behavior and very accurately, that complex system gives us an opportunity to like really figure out how to even analyze a complex system. Like, so it's, to me, that's a huge bonus from these networks, because neuroscientists, I think, have been trying to do both things at the same time, like build the complex system and then figure out how to analyze the complex system. And here are networks that are already built up, and you can formulate like different theories based. And I think, to me, that's like a huge advantage of having these networks. And they really become like the starting points and maybe base hypothesis for a lot of these neuroscientific experiments. So that's kind of like, at least how I have been mostly getting excited about the crosstalk between the two fields.
We talked about how there's this kind of archaic fallacy, I suppose, for, naming a brain region, giving it a role, right? And the modularity of the brain, prefrontal cortex does X, that sort of thing. And we've talked about, well, I guess I mentioned about how language actually limits us in some sense. Do you feel like we understand what intelligence is? Do we have the right notion of what intelligence even is to start trying to, to continue trying to build, quote unquote, AI?
I don't. I don't know which scientist we are thinking of. Like, I think for me, I probably don't have a complete understanding of what intelligence is, but I have a fair enough understanding of what kind of intelligent behavior I would like to build models for. And so that's where I'm just a kind of the engineer in me, maybe like talking, because I know what problem I have defined. I want to know the solution. So like this kind of tasks that are slightly above, recognizing an object and like trying to figure out like what different agents are doing in an environment, or like trying to predict what might happen next. Like these kind of behaviors, I think, are fairly intelligent behaviors. And my goal is to build models and try to figure out how the brain is actually trying to solve that problem. So in that way, I'm fairly happy about the definitions of intelligence. But then again, we'll get into trouble. Like I'll get in trouble saying, what is intelligence? Maybe like the typical like IT, scores, or, IQ scores. I think they're heavily debated. And so I just feel like what I want to say is that we can keep debating about what is the right score, what is the right way of quantifying intelligence, but we have to do it in some way if we want to have any measurable progress. So I have defined it in some way, and I will keep, improving that definition and, expanding on that definition. But I think, intelligent behaviors are, to me, not that controversial. Anything that I can do that my 3-year-old son cannot do almost seems like a definition of like a little bit more intelligent, but he might be learning faster than me. So at this stage, so like the kind of definitions like that maybe that exist, but like, yeah.
You have a 3-year-old?
I do have a 3-year-old.
Is that the only child?
Yeah, he's our only child.
Oh man, that's kind of a hard patch going through and starting a new job and all that. So I feel sorry for you. I mean, it's a wonderful thing, obviously, but it's challenging early on. So
it's yada yada yada.
Yep. Are you? Go ahead.
I must say, like, I'm happier on average. Like like after taking into consideration everything around the child, I think overall I'm happier that we have a son. That's the most I will say about this.
Yeah, okay.
It's tiny. It's like a p, p equal to 0.04.
Yeah, but, right. I used to draw this a pie chart where that I would show people, like, do you like having kids? And it's like 51% yes, right? 49 no. But yeah, all right. Maybe I'll cut this because I sound like a real jerk. Are you hiring in the lab? Are you looking for students? What's the situation?
Yeah. I'm definitely looking for postdocs and grad students to work together in my lab. So I think if folks are interested, I mean, the grad students they're basically going to be recruited through York's graduate program.
Yeah.
And the postdoctoral candidates, I think I'm like just going to talk to them individually and then see where the sort of alignments lie. And yeah, definitely, like, so if folks are interested in whatever we spoke about, and maybe if they read some of the papers and think there are interesting directions that they might want to pursue, I'm definitely interested in talking.
He's the future of neuro AI, folks. It's this has been a lot of fun, Ko. Congratulations again on the job, and gosh, I'm just excited for you. It sounds like you have a lot to pursue, and things are looking up. Not that they were ever looking down, but congrats.
Yeah. Thanks, Paul. I mean, there has been a lot of promises made. I feel like I'm kind of like making a lot of promise, and I hope I am able to deliver. I feel like as long as I can quantify what those promises are, I can tell you in maybe a year where I have been, how much I have, delivered. So
we'll check in a year. We'll check in.
We should check in. But yeah, I'm excited. I think this is worth doing. So I feel like I'm all excited to get on with it.
This has been great, Ko. Thank you.
Yeah, thank you so much.
Brain Inspired is a production of me and you. I don't do advertisements. You can support the show through Patreon for a trifling amount and get access to the full versions of all the episodes, plus bonus episodes that focus more on the cultural side but still have science. Go to braininspired.co and find the red Patreon button there. To get in touch with me, email paul@braininspired.co. The music you hear is by The New Year. Find them at thenewyear.net. Thank you for your support. See you next time.
The stare